Hello and welcome to this next lecture on sound and structural vibration. This is where we stopped last time. We were looking at the correction term and it has this behavior. Below coincidence, it has a purely inertial loading on the structure, and beyond coincidence it has an oscillatory behavior. Okay, there are points where it is stiffness like, there are points where it is inertia like, okay, and there are points where cot kya goes to 0, so it adds no correction and hence uncoupled and coupled cross each other. Say these are critical points I said. So let us see what is this, what are these two critical points. Okay, critical points. So first critical point first is when cot kya is equal to 0, which means cosine kya is equal to 0, which means kya is of the form, let us say twice n plus 1 pi by 2, okay, and therefore ky is equal to twice n plus 1 pi by 2a. Okay, so let us take the first fellow, which is n equal to 0, let us say. Okay, then kya is equal to pi by 2a, okay, and which is equal to twice pi by lambda y, right. This is the relation between lambda and wave number. Okay, ky is the y directional wave number, so lambda y is the y directional wavelength. Okay, so if we now do this, it means what? It implies that lambda y is equal to 4 times of a. Okay, so 4 times of a, we will picturize this, we will picturize. Okay, so I have the top surface of my waveguide, I have the bottom flexible surface of the plate. Okay, now at the top surface my pressure will have a 0 gradient because velocity is 0. Okay, so now let us imagine this is the 0 pressure line, suppose. Okay, let me take it smaller, sorry, let me take it smaller, else I will take up the whole page. So let us say this is my structural acoustic waveguide bottom flexible plate. Okay, and then at the top, so this is a mean pressure line, 0 pressure line. So at the top the velocity is 0, so I will have peak velocity. Okay, now I have to come up with lambda, this is a, okay. Okay, so this lambda is 4 times of a, how can it be? So this is total lambda, you can see that, right, lambda y, one full cycle, and it is also showing that it is equal to 4 times of a. So what does it mean with when you enforce this relation such that a is a fourth of lambda, the pressure here goes to 0. So this is lambda y by 4. Lambda y by 4. So first, by being lambda y, you have to show one wavelength. On top of that, its relationship is with A is it is 4 times of A. If you enforce that relationship, by the time it reaches the bottom flexible plate, the pressure is 0. Okay, so that's the critical point. So when pressure is 0, the structure will not see the fluid, does not see the fluid. And for a brief moment in frequency gets uncoupled in the presence of the fluid, and therefore the two curves cross. Okay, so now if I go to the next level, which is, let's say, ky is equal to 3 pi by 2a, okay, and then start computing. My a will be equal to 3/4 of lambda. Okay, so how will the picture actually look? The picture will look like this. It will start off, this is the mean pressure line. It will start off and it will sorry, see, it will start off, it will come and go to 0 here like this. Okay, then you will have the wavelength, full wavelength. This is A is 3/4 of lambda and so forth. So every time you have a 0 pressure at the flexible plate surface, so the plate doesn't see the fluid and a crossover occurs. Okay, so this is one critical point. The second critical point is when cot ky goes to infinity, cot kya goes to infinity. Okay, we have seen those pictures, right? We have seen these regions. Cot kya goes to infinity. So what happens there? Okay, so cot is cosine over sine, which means now sine kya goes to 0, okay, which implies that kya is equal to n pi. Okay, so let's take the first one, which is kya equal to pi, or ky equal to pi by a, okay. So ky is equal to pi by a is equal to twice pi by lambda y, implies lambda y is equal to twice of a. So now if I plot it like this, this is my top rigid and this is my bottom lower flexible, okay, and so I start off here. Let me, this is a mean line. So I start off at the top, okay, it is a rigid plate, so I'll start with pressure gradient 0, so it will start with a high pressure, then it will come, it will have again a peak pressure, okay, and then it completes the wavelength. So this is full wavelength lambda y. okay, and it is what equal to twice a now. But what is the net result? You can see here del p del y is 0, which is equal to Vy. So the velocity here is 0, the fluid velocity. So the fluid C is plate velocity 0, okay, and the structure sees fluid velocity as 0. Okay. Hence, it is a region where one is seeing a high impedance from the other. Okay, one is seeing a high impedance from the other. So if we look at this equation, kx to the power 4th over kb to the power 4th is equal to 1 minus epsilon cot kya by kya. If we look at this equation, okay, now we have to balance this equation. We have to balance this equation. Okay, that means what? Finite values of kx. We have to find finite values of finite possible values of the coupled wave number. Okay, and therefore when this is blowing up, when this term is blowing up, going to infinity, the one that prevents complete loss is this epsilon. Epsilon will balance out the growing term. Okay, the epsilon, which is a small parameter, will balance out the blowing up of this cot term, so that this can be balanced, this equation can be balanced. So there is a finite value of kx, finite possible value of kx. Okay. In other words, based on epsilon, the degree to which cot kya blows up, that means cot kya exactly does not go to infinity, will not be allowed to go to infinity. Why? Because ky is square root of k square minus kx square. Okay. So how close kx will get to ky will depend on epsilon, such that the blowing up is prevented. Okay. So such that so that equation gets balanced and you get a finite possible value of kx. You have to find a suitable asymptotic expansion. Asymptotic expansion. Okay, so that's what is happening when when you do the full coupled calculations. Okay, I'll summarize this again when we get a chance. Okay, so but right now these are the two critical points and how they behave and how kx behaves accordingly. So now the next step here is, we have looked at flexure, right? We have to look at coupled acoustic wave number. Coupled acoustic wave number. Coupled acoustic wave number. Okay, we'll just look at the plane wave. We'll just look at the plane wave, because by now you know how to deal with the physics and the mathematics. Just look at the plane wave. So the equation I have is EI. Oh, let me change the page because I will need it for arguments. Okay, so the equation I have is ei kx fourth minus kb fourth, I have written in a modified form, is equal to minus omega square rho by square root of k square minus kx square cot of square root of k square minus kx square into a. Okay, we will write it, this is for kx less than k, we will call it some equation a, okay, which is also now equal to omega square rho by square root of kx square minus k square. Please note the switch, and this is cot hyperbolic square root of kx square minus k square into a. We will call this b. Okay, so you can see that the b equation or the a equation is for below omega equal to 1, below coincidence. Okay, and b is above coincidence, above omega equal to 1, above coincidence. Okay, so we are looking at kx close to k, which is the plane wave. Why do I assume this? Why do I assume? I don't assume this. Using asymptotics we have found this. Okay, this was found using mathematics, so I am stating it. Okay, and now I am looking, because we are going to explain the result. Okay, the mathematical result is already derived, so I am explaining the result. So this was found out earlier. Okay, and we are looking at kx close to the acoustic wave number, and how does it look like? Just refresh. So this is my acoustic plane wave, okay, and this is my, let's say, flexure. My coupled plane wave looks like this. It's below here, this is coincidence, and it's above here. Okay, so let us explain that. Okay, so let us look at if kx, if my kx okay approaches k, kx approaches k, okay, then we are looking at equation A. Okay, equation A, and what happens? Equation A, cot is has an argument which is going to 0. Okay, so the right hand side RHS tends to infinity. Okay, Okay. Sorry. We are looking at equation B here. Okay. So as kx approaches k, okay, and in equation B, the right hand side approaches infinity, okay, and it's positive. It is positive. Positive. So I am going towards positive infinity. Okay. Now on the left, how is this possible? On the left, okay, on the left, this is possible by EI should kx is greater than k. Okay, on the left it is possible by EI that is made to tend to infinity, which means the plate is stiffer. Okay, so as my plate becomes more and more stiff, okay, above coincidence my kx will start approaching k, okay, and that's how the both sides will balance. Okay, so here again, I mean infinite stiffness cannot be achieved, but that's the mathematical limit. So if you manage EI tending to infinity, the left hand side will go to infinity and the right hand side goes to infinity, then my kx exactly lands on k, the plane wave. Okay, so this is above coincidence. Okay. On the other hand, the same argument holds if EI is reduced, that means the stiffness is reduced, the plate is becoming more flexible. Okay, the left side reduces, okay, and the coupled wave number kx moves away, and above k. Okay, so moving away means kx increasing, which means lambda x decreasing, which means the speed decreasing, speed of the wave decreasing. So this is a story above coincidence. Okay, now below coincidence, again we will keep kx close to the plane wave k. Okay, then I will need to write the equation for clarity. EI kx fourth minus kb fourth is equal to minus omega square rho by k square minus kx square cot of square root of k square minus kx square into a. Okay, here kx is less than k. This is the a equation below coincidence. Okay. Now again, if the value approaches infinity, okay, and kx is approaching k, okay, the cot value approaches infinity and this is approaching 0. Okay. Now looking at the left, on the left side, I have to approach negative infinity. I have to approach negative infinity. Okay, I have to approach negative infinity. Then what happens? What will do that? If I open this term out here, I have ei kx fourth minus m omega square, okay, is equal to the right hand side. This right hand side is reaching minus infinity, okay, and therefore the only way that can be balanced by the left side is if mass tends to infinity. That means the plate density goes up. Okay, or the fluid if this is the original plane wave, this is the original uncoupled flexure and this is coincidence. So here the fluid sees the structure as a stiffness. Okay, if it gets stiffer and stiffer, the wave number comes down, and here the structure is infinitely stiff, whereas here the fluid sees the plate as inertia. As inertia increases, plate inertia increases, we approach again the uncoupled. So this is infinite inertia of the plate. As the inertial value drops, the wave number starts to drop. Okay, so it is as though there is infinite inertial loading from the plate, and that's when you get the uncoupled plane wave. For any other finite value, the wave number drops. Okay, so the inertial loading drops, and so the wave number drops, and therefore the lambda x goes up, so the speed goes up. The speed of the wave goes up. Okay, so I will stop here. We are running out of time. I'll continue from here in the next class. Thank you.